Polar covalent typically have electronegativity differences between, so there's going to be less than 1.67 and 2.5. So 1.67 to 0.5 is the difference in electronegativity. So when a bond is polar covalent, you have one side that is partially negative and one side that is partially positive. So what this means is they're not full positives and negatives like you get with ionic compounds. It means that they share electrons unequally. So the polar covalent bonds have stronger bonds between the molecules. That's that dipole-dipole. And while ionic compounds have high melting and boiling points, they have low vapor pressures, so on and so forth, and they're solids at room temperature. Polar covalent are the next step down. So they have medium melting and boiling points, and they can be solids, liquids, or gases at room temperature. And the larger the molecule, the more likely it is to be a liquid or a solid. So that has to do with size. So the small compounds will be gases, and then medium compounds will be liquids, and then large compounds will be solids, polar covalent. So let's go down here and let's discuss how we know this. Here is my electronegativity scale. Remember that we have our hot spots in the corner here. So fluorine is the most electronegative. It has the highest effective nuclear charge. That's that Z. And it has the smallest radius. So the nucleus is closest to the action. Fluorine is the bossiest guy. He will take electrons from whomever he wants to. Then notice it is a sliding scale. So if you think about a line that you can drag down, so the closer you are to fluorine, the more electronegative you are. Oxygen's number 2, then comes nitrogen and chlorine, so on and so forth. The further you are away from fluorine, so if you think about sliding this bar down till you get to francium down here, the further you are away from fluorine, the least electronegative elements will reside down here in this corner. So when we form molecules, you can determine, at least in a general sense, how polar the molecule will be by how far away are they from each other on the periodic table of the elements. So remember, do not refer to their position on the periodic table of the elements as the reason why. That just gives us the information. And when you're describing why this is, you're going to say that fluorine is the most electronegative, not because it's in the upper right-hand corner of the periodic table of the elements. It's because it is the smallest, most electronegative, has its nucleus closest to the action, and therefore gives it the ability to take electrons from anybody that he wants. So let's go down here and see that they summarized it like this, but this is not a hard and fast rule. So ionic, greater than 1.67, covalent is between 0.5 and 1.67, and nonpolar covalent is typically considered less than 0.5. Remember, the only truly nonpolar covalent molecules, it's a sliding scale. The only truly nonpolar covalent molecules here are going to be diatomic elements, or a bond between two identical elements, or compounds with symmetry. And everybody else is going to lie somewhere on this scale until you get to the greatest electronegativity difference, which would be between francium and fluorine, and everybody else lies somewhere in between. So bond polarity and electronegativity is a measure of the nucleus's attraction or pull on the bonded electron pairs. When the two nuclei are identical, the sharing is equal, and that's nonpolar. When anything greater than that is going to have a level of polarity to it. Until the electronegativity difference becomes too great, then it will be an ionic bond and will result in an exchange of electrons. So let's go and see what this means for us. So most compounds are covalently bonded, especially carbon compounds. So there's a couple things that we need to discuss here is when you figured out that you're going to be forming a molecule or a covalent bond, you want to remember that the octet rule is what usually governs building of molecules, especially with carbon. Now, there are a few exceptions. If an element has a D sublevel, then they can expand the octet rule. But usually when you're dealing with carbon compounds, you always have that octet rule. And they love to. So for polar covalent and nonpolar covalent, they love to use the same kinds of bond. So if you are polar covalent, the most polar covalent bonds will be between, remember, hydrogen bonding is fun. So it will be between nitrogen and hydrogen, oxygen and hydrogen, or fluorine and hydrogen. Those will result in hydrogen bonding between molecules. Remember, I don't like the term hydrogen bonding because it's not actually bonds, but that's how we describe, that's what it's called nonetheless. And whenever they're doing nonpolar bonds, they typically use carbon molecules. So if you see a carbon-hydrogen bond, we're going to consider this nonpolar, and then the intermolecular forces between two different molecules will always be London dispersion forces. In carbon compounds, we can have single bonds, which are one pair of electrons shared, double bonds, which is two pairs of electrons shared, and triple bonds, which is three pairs of electrons shared. So when it comes to carbon, let's describe what's going on here. You have a carbon-carbon single bond. So carbon has 4 valence electrons. Let's just draw the dot diagram for carbon. It has 2 s and then 2 p electrons. But when carbon's going to go to form a bond, a little bit of energy will need to be added to it. And when you add the energy, it does what's called hybridization. So let's see what that looks like. Carbon, this is our s electrons right here. Remember, they have to have opposite spins in order to be in the same orbital. And here's my p electrons here. When I add a little bit of energy to it, here's what happens. This electron here is what's called promoted. So that means that he's going to jump up into the higher energy level like such. So I have, instead of 2s and 2p, we hybridize into 1s and 3p. And then, just like when you take a cup of hot water and add it to a cup of cold water, you don't get parts that are hot and parts that are cold. They mix together and become medium energy. And this is called sp3 hybridization. So I want you to think of sp3 hybridization as carbon single bonds. So each carbon forms 4 bonds. If they are all single bonds, we're going to call this sp3 hybridized. Now, if we're going to form a double bond, one of these p electrons is going to be left like that to do that side-to-side double bond. So you will have one S and two P that hybridize, and one P that stays like that to be the double bond. So this is going to be sp2 hybridization. And this is going to be for double bonds. So if you have a carbon that is double bonded like this, this will be sp2. When they are all single bonds are called sigma bonds. And when the double bond is formed, it will have three sigma bonds. Notice the superscripts add up to three single bonds, and then this double bond is called a pi bond. So a double bond is a sigma bond and a pi bond together. What I mean is a sigma bond is a head-to-head bond where the electrons are shared like such. These electrons are the shared pair. When I have a double bond, it's going to be a shared pair in here, and then the side-to-side bond is going to be your pi bond, like such. And then the last case scenario is when we have a triple bond that will have two sigma bonds and two pi bonds. These P's will be our pi's. These S's will be our sigmas. So we will have one S and one P that hybridize, and this will be sp hybridization. Two of the electrons will stay as P to pi bond. So sp is going to be one electron there. These two, that's an S and a P. Notice the superscripts add up to 2, and that's going to be 1, 2 side-to-side pi bonds, like such. It's a triple bond. So triple bonds are always considered sp hybridized. So that's going to be a carbon. Notice still 4 bonds. Carbon has 4 valence electrons, going to form 4 bonds. And a triple bond consists of 2 pi bonds and 1 sigma bond. So this is a summary of the covalent compound concepts that you need to know. So for covalent compounds, the electronegativity is in play. A large difference in electronegativity will give you polar bonds. Typically expect to see those as nitrogen, hydrogen, oxygen, hydrogen, or fluorine, hydrogen bonds. Non-polar covalent, you need to think about whether it is a sp3, sp2, or sp hybridized. And the concepts you are going to come up with those is going to be sigma or pi bonds. Sigma bonds are single bonds. Double bonds are a sigma and a pi. Triple bonds are a sigma and 2 pi's. That is a summary of the concepts you would need to know in order to describe covalent compounds. Next, we will go over how to build these structures.